talked about air masses, we're going to talk about what happens when two air masses run into each other. That creates a lot of really interesting weather, and that creates what are called fronts. Now, this is based off of pages 235 to 244 in the textbook. So if you're following along in the textbook, that's where you go. Again, it might vary a little bit depending on your edition, but that's what that is. So let's talk a little bit about fronts. Now, fronts are the transition zone between two air masses. Now, this is very important because when I talk with a lot of students, they think that a front is an air mass. Repeat it with me and then repeat it 1,000 times more. A front is not an air mass. Pause this video, repeat it 1,000 times. A front is not an air mass. A front is not an air mass. And it's the transition zone between two air masses. So it's like the border between two air masses. So when you tell somebody that they're under a cold front, you're basically saying to somebody who lives in Los Angeles, oh, you are on the US-Mexico border. Which isn't true. You're 100 miles away from the US-Mexico border. So with that said, a front is not an air mass. A front is the boundary, the transition zone between two air masses. And the United States is the prime breeding ground for fronts. And the reason why is because we have tropical air masses to our south, polar air masses to our north. And those air masses are constantly bumping into each other, creating fronts. Now, what actually happens along a front? Why do fronts actually give us weather? Or interesting weather anyway? Well, the reason why this happens is when two air masses collide into one another, that's what a front is, the warmer air mass overruns the colder air mass. The warm air mass rides up and over the cold air mass. Now, if you've been paying attention the last few weeks, you remember what happens to air as it rises. It does three things that we really care about. It expands, it cools, and moisture condenses. That condensation produces clouds, which oftentimes produces precipitation, and hence, a lot of precipitation occurs along fronts. So the warm air overruns the other air, the colder air, expands, cools, and condenses, and we get precipitation. As a result, these air masses have vertical extent too. An air mass isn't just present on the surface of the Earth, but it actually expands up into the atmosphere. And therefore, when these air masses collide, they bend into each other higher up in the atmosphere. And this process is again called overrunning. And the upward extension of one of these boundaries, this border between the two air masses, is called a front. Oftentimes referred to in the upward extension, oftentimes referred to as a frontal zone or frontal surface. Here's an example of a series of fronts. So here you have, in front of everything, in front of the front, no pun intended, you have a warm air mass. Meanwhile, pushing in is a cold air mass. As this cold air mass pushes in, it takes this warm air and it pushes it up and over. And then eventually what happens is an even colder air mass comes in from behind and it pushes this cold air up and over. Because even though this air here is cold, it's still warmer than the very cold air behind it. And this is just an example of two different fronts and what happens vertically along them. The warmer air is pushed up and over. And then this surface, this boundary between the warmer air and the colder air, is what's called a frontal zone or frontal surface. Now, there are four main types of fronts, and we're going to talk about all four in brevity today. They are cold fronts, warm fronts, stationary fronts, and occluded fronts. Let's jump in. First, let's do the easy one. Stationary front. A stationary front is a boundary between two air masses that aren't moving. As a result, it's called a stationary front. There's no movement of air along a stationary front. The warm air is in place, the cold air is in place. One isn't moving relative to the other. Hence, the front is stationary. Now, once these air masses do begin moving, the front transitions into either a warm front or a cold front. But as long as the air masses aren't moving relative to each other, we have a stationary front. All right, now with that taken care of, let's talk about cold fronts. Cold fronts are a boundary where warm air is moving away and cold air is moving in. And cold fronts actually can produce some very interesting weather, even more interesting than the other fronts we're going to talk about. And the reason why is because when that cold air moves in, it pushes the warm air out, causing pretty sharp drops in temperature. And in fact, I actually experienced one of these one time when, in a 20-minute time period, the temperature dropped by over 25 degrees. That's a substantial cool down in a very short period of time. And it was because a cold front blew through. At the beginning of that 20-minute period, I was under a warm air mass. At the end of that 20-minute period, I was under a cold air mass. Sometime during that 20-minute period, a front passed over. And that was it. Now, so along a cold front, warm air is being pushed away by cold air. And cold fronts are shown on weather maps as blue spiky lines, and these spikes point in the direction that the front is traveling in. So when we see, and let me grab a pen here, when we see, and I'll actually use black, when we see this particular graphic here, these spikes are pointing in the direction that the front is traveling in. So the front is heading generally in this direction. And this is important to know because weather forecasters want to know how the weather over here might change. If we have a cold front approaching, we can confidently forecast that, hey, cold front's approaching, temperatures are probably going to drop. Now, as the cold front moves in, as that cold air mass behind the front moves in, it actually forces the warm air to shoot straight up at a very steep angle. As a result, all of this warm air goes straight up. This creates a lot of very, very good lifting. And if the air aloft is conditionally unstable, that lifting is going to create cooling and condensation, which is going to create towering cumulonimbus clouds. As a result, right along cold fronts, the weather is usually very stormy. And in fact, most of the rain that we get here in California is because cold fronts blow through. And those cold fronts give us a 6 to 12 hour period of heavy rain. A 6 to 12 period of heavy rain. And so stormy weather is typically present ahead of one of these cold fronts. As soon as the front passes, the storms quickly subside and the weather becomes a lot nicer. A lot colder, but a lot nicer. So this is essentially what happens. As the front is charging in, it pushes that warm air straight up, creating towering cumulonimbus clouds. Now, because of this, thunderstorms are usually very common. I'll use a different color here. Thunderstorms, like these ones here, we'll actually take a look at weather radar in the next module. thunderstorms are usually denoted with these areas of yellows and reds. And these are usually common ahead of a cold front. And oftentimes these thunderstorms can become severe, creating heavy rain, hail, and even tornadoes. And we'll talk more about that in the next module. But cold fronts create a lot of lifting, which can create a lot of these thunderstorms. Now, how can we identify where a cold front is present on a map? Well, all we have to do is look at a narrow region where weather conditions quickly change. So let's talk about this. The area ahead of the front is the area where the blue spikes are pointing at. And this is because this is where the front is traveling. Since the front is traveling in this direction, this area here hasn't experienced it yet. If you take a look, these areas here are all experiencing relatively warm temperatures in the high 50s. Winds are coming from the west-southwest. So we have southwest winds and warmer temperatures. As soon as the front blows through, we notice a quick decrease in temperature. We also notice that the winds shift. Rather than coming out of the southwest, they quickly shift to the northwest. And then temperatures drop. This is one of the ways we're able to identify the presence of a cold front. If ahead of the front, temperatures are warm and winds are coming from the south or the southwest, that's indicating a warm air mass. Once the front passes, behind the front, the weather becomes substantially colder, winds shift to the north or the northwest, and as a result, and then this is because the air back here is much colder. Now, most cold fronts that we experience here in the northern hemisphere and here in the mid-latitudes usually blow from west to east. Why? Because that's the direction that the jet stream blows in. However, there's one special type of cold front that occurs along the eastern seaboard of the United States, and this is what's called a backdoor cold front. Basically what happens is cold, moist air, right here, from the North Atlantic sometimes blows in to the northeast of the United States, and this causes an air mass boundary between warm air near the south and cold air near the north. This kind of front actually travels from east to west, hence the term backdoor cold front. All I really want you to know is that a backdoor cold front travels from east to west. It comes off the east coast and travels onshore. That's all I really want you to know. And they're common over the northeast of the United States in a region called New England. That's really all I want you to know about them. If you don't know any more than that, you're good enough. All right, now what about warm fronts? Now, warm fronts are different from cold fronts. And they're different because instead of them being a boundary between retreating warm air and advancing cold air, they're the opposite. They're instead the boundary between retreating cold air and advancing warm air. Warm fronts are a boundary where cold air is being pushed away and warm air is coming in. And they're shown on a weather map by a red line with these humps pointing in the direction of travel. So in this case, the warm front is traveling this way. And as the warm front passes through, cold air is pushed away and warm air moves in. Now before I move on though, I do want to mention one very important thing about warm fronts. They travel a lot slower than cold fronts. Here's why. Cold air is very dense air. The colder the air, the denser it is. As a result, when cold air comes in and pushes warm air away, that's basically the equivalent of you kicking a beach ball filled with just air. Your foot is a lot denser than that ball, so even a light kick could cause that ball to travel really far and really fast. On the other hand, along a warm front, you have less dense air pushing really dense air away. If you've ever had an experience where maybe you have a little brother or a little sister, and I'm talking like 5, 6 years old, and they're trying to push you, and you're much bigger than them, are they going to push you very far, very fast? No. Well, that's basically what a warm front is. Along a warm front, this cold air mass is you, this warm air mass is your little brother or sister. They can push you, but they're not going to push you very fast. They're not going to push you very far. As a result, these warm fronts travel very slowly. Another good analogy, that same kickball analogy I mentioned, imagine that same ball, but now instead it's filled with wet sand. Try kicking it. It's not going to travel very far, and in fact, if you try to kick it hard, you're going to break your foot. So if you do try that demonstration, don't try to kick it really hard. Kick it very lightly. But you'll notice it's not going to travel very fast or very far. So again, warm fronts travel much slower than cold fronts. That's going to become important in a moment. Now, as a warm front passes over, that cold air mass is being pushed away, and a warm air mass is coming in behind it. As a result, as a warm front passes, temperatures warm substantially. Temperatures warm substantially as a warm front passes. Now, along a warm front, because that cold air is much denser, the warm air travels up it at a very, very, very light angle, very shallow angle. A much more gentle angle than the cold front. Now, this creates precipitation, but it's usually much more light than along a cold front. However, that's not to say that warm front weather isn't interesting. There's one thing that's very interesting about warm fronts. Because a warm front is occurring, or because a warm front is coming in, you get this situation where, I'll try to draw it to the best of my knowledge, or, well, best of my abilities. So, let's say here's the ground, and let's say you have a warm front that's about to come through. And the warm front's going to look something like this. Down here's the cold air, and I will try to write that here, that this is cold air. Sorry about that. Meanwhile, here aloft you have warm air. Those look terrible, but hey, they work. Well, you get this interesting situation where you have warmer air aloft than at the surface. This is an inversion. Now, what's interesting about this inversion is if you have any clouds that have formed in this warmer air, they can rain down, and as they rain down, once they travel through this frontal surface and into the cold air mass, they can freeze, producing sleet and freezing rain. So if you remember back in Module 4 when we talked about sleet and freezing rain, well, this actually is how that happens. It happens because you have an inversion aloft, you have this warm air aloft, which allows snow to melt, and then as soon as it passes through the front into this cold air, it freezes again, forming sleet or freezing rain. So warm fronts are where we get that sleet and freezing rain. We call this wintry precipitation. So if I ask you that on the quiz, just know sleet and freezing rain happen along warm fronts. And again, they happen along warm fronts because you have this warm air aloft here, which allows for rain to melt, or for snow to melt into rain. And then as it passes through to this cold air mass, right here, as it passes through this cold air mass, it freezes. Man, my penmanship here is terrible. Sorry about that, but it freezes again into sleet or freezing rain and so on. So, if you were to describe the conditions before, during, and after a warm front, usually before the warm front, the weather's cold. Winds are usually coming from the east or the southeast, and that's because that's where the center of the cold air mass is. And usually you'll get this progression from snow to sleet or freezing rain over to rain. Then the front passes, and as soon as the front passes, you quickly get an improvement in conditions. One other thing I should mention is cold fronts typically travel from northwest to southeast. Warm fronts, on the other hand, typically travel from southwest to northeast. Why? Because warm air is closer to the poles. So usually this warm air and this warm front is traveling from south to north rather than from north to south. And it pushes that cold air away. I do have a handout online, and you're going to need to read it before you do this week's activity, that actually explains a little bit more the conditions before, during, and after a frontal passage. Before a warm front, winds are usually coming from the east or southeast. You have cold temperatures, low dew points. Then the front passes, temperatures go up, dew points go up, conditions quickly improve. Now, warm fronts and cold fronts usually don't operate independent of each other. Rather, they're usually in tandem together. They're usually in tandem together, and they're part of what's called a mid-latitude cyclone. We'll talk more about mid-latitude cyclones in the next lecture, but this is where warm fronts and cold fronts exist. They exist along mid-latitude cyclones. As a result, you have a warm front that's creeping along very slowly and a cold front charging ahead really fast. Eventually, the cold front catches up to the warm front and overtakes it in something called an occlusion. Basically, what happens in an occlusion is the cold front and the warm front essentially zip up. They zip together the same way that a zipper on your dress or your pants or whatever works. They just zip together. Now, in between the warm front and the cold front, there's this warm air mass between them. We actually call this the warm sector. Ahead of the warm front, the weather's usually cold. Behind the warm front, the weather's usually warm. Ahead of the cold front, the weather's usually warm. Behind the cold front, the weather's usually much cooler. Well, as an occlusion occurs, it skips this middleman. It skips this warm sector. And you simply just transition from one cool air mass to another cool air mass. And this is actually marking the beginning of the end of a mid-latitude cyclone. And we'll talk more about that next time. There are actually two types of occluded fronts. The first one is what's called a warm air occlusion. The second one is called a cold air occlusion. A warm air occlusion occurs along the US West Coast. Here, ahead of an occluded front, the air is usually very cold. It's continental polar air. And it's usually very cold and very dry. Then the occluded front travels through, and behind it you have a slightly warmer moist air mass. Maritime polar air comes in, and temperatures usually rise a little bit. On the other hand, a cold air occlusion, these are common on the east coast of the United States, occurs when you have a cool moist air mass, usually coming in from the Atlantic, and it's being pushed out of the way by a cold, dry continental air mass coming in from the interior United States. So this is a warm air occlusion. You have cold air present over the Rocky Mountains and over the interior of the country. And then this not as cold, cool air comes in and moves out of the way. Comes in and it pushes that cold air out of the way. Along a cold occlusion, the opposite happens. You have this cooler maritime polar air being pushed out of the way by much colder continental polar air. So what I really want you to know is that warm air occlusions occur when continental polar air is being pushed away by maritime polar air, and they're common on the west coast of the United States, whereas cold air occlusions occur on the east coast of the United States, and they occur when maritime polar air is being pushed out of the way by continental polar air. That's a mouthful, so if you need to rewind and go over this another time or two, don't beat yourself up over that. And that's it for this lecture. The next lecture we're going to talk about the life cycle of a cyclone. Until then,